Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hey y'all, welcome back to AP Physics 1. We're in Unit 5, one of my favorites, Torque and Rotational Dynamics. I know we've talked about this already. Some students don't like it. My advice to you is spend some time on these words, their symbols and their units and their equation, and get more familiar with it because it is Greek letters. Some of the letters don't go with the units, don't go with the word. It just seems like it's not as logical as in that first semester. So spend some time with this and I promise you it will not be wasted. All right, hopefully you'll love it as much as I love it after all that. So here we go. Linear acceleration. We're going to do this video just like we did the last two. This is our third video in this unit. First one was linear displacement versus angular displacement, then linear velocity versus angular velocity. Now we're going to do linear acceleration versus angular. My students for over a decade now have said it just makes it click a little bit better when you hear it, when you see this and it's introduced with something you're already familiar with. All right, so we're just going to get started. I already have this started here with linear acceleration because you've been doing this for a semester. You're a pro at this point. The symbol is a lowercase a with a vector sign over it because it is indeed a vector. The unit was a meter per second squared. Why was that? Because the equation for acceleration is the change in velocity over time. Velocity was in meters per second. If you remember, we're dividing by another second. You get meters per second squared. All right, perfect. Now let's go over and talk about angular acceleration. And by the way, remember, this is always that change in velocity over time when you're talking about linear. If you've got a car going down the road and it goes from 5 miles per hour to 25 miles per hour, then you've had a change in velocity over time and you've got acceleration. Okay, very similar concept with angular acceleration. All right, let me go through this and then I'll show you what it really is. The symbol is a lowercase alpha. That actually makes sense because acceleration is an A. That one makes sense. So it's a lowercase alpha, and my students have always liked to call it the fishy thing. But anyway, the fishy thing. The unit, remember when we're measuring linear, we're using meters for displacement. But when we're measuring in rotational, we're measuring radians. So this is going to be radians per second squared. And we abbreviate radians as rad because rotational motion is rad. Hopefully you're going to feel like that before we get to the end of it. And our equation is that angular acceleration is the change in that angular velocity over time. Just like how linear is the change in linear velocity over time, angular acceleration is the change in angular velocity over time. All right, so what does that mean? You're like, Ms. Colson, I really need to understand what that means. So let's talk about that. All right, I have a little device I've made up here, not my fancy tire in the classroom, but anyway. Remember, angular velocity is just about how fast it spins. So this spins, right? If it's spinning really fast, it has high angular velocity. If it spins slow, it has lower angular velocity. All right, so angular acceleration is just a change in that angular velocity over time. So in other words, I can be going really, really fast and then start slowing down. I now have a change in how fast I was spinning because that's what angular velocity really is. How fast are you spinning? I was spinning really, really fast and then I started slowing down. Change in my angular velocity, change in how fast I was spinning over time. So now I have angular acceleration. Same thing if I was going really slow and I start speeding up. Again, I have a change in my angular velocity, a slow spin to a fast spin. All right, so I have angular acceleration. Now, just like when we talked about in the last video, how when you have angular velocity, you can have tangential velocity. You know, the wheels on the bus go round and round, but the bus itself goes down straight down the road, that tangential velocity, tangent to the wheels. All right, it's the same thing with tangential acceleration. Let me go ahead and give you the symbol first. The symbol we use is an A with a lowercase t. All right, that's your your tangential acceleration symbol. The unit, and that's just a little subscript t there. The unit is going to be the same as our linear. It's going to be meters per second squared. And our equation is going to be that our angular acceleration, I am so sorry, let's start that on the right acceleration. Our tangential acceleration is equal to that radius of your wheel or whatever you have times your angular acceleration. That's going to be equal to your tangential acceleration. All right, now what is tangential acceleration? Let's talk about that. Man, that's hard to say 5 times fast there. Tangential acceleration is linear acceleration caused by rotational motion. And specifically caused by angular acceleration. So rotational motion really meaning angular acceleration. Okay? Now, oh, that was terrible writing. Sorry about that. Speaking of rotational, that kind of looks like I'm rotating there. Anyway, did not mean to do that, sorry. All right, so now let's talk about this car. I got the wheels on the car going round and round. They're spinning. They have angular velocity. But now let's see what happens if I have this car where the wheels are turning slowly and then they speed up. All right, so they're turning, they're rotating slowly, they're spinning slowly, and then they spin faster and faster. All right, that means I had angular velocity that was low, and now I have higher angular velocity. That change in angular velocity over time, that means that I have angular acceleration. My wheels are spinning slow and then they're spinning fast. Well, if you notice about the linear motion of this car at the same time, the wheels, as the wheels are turning slowly, spinning slowly, and then spinning faster, the car is actually accelerating. It is moving slow, and then it speeds up. All right, those are linked. The reason that that car is having a change in the linear velocity over time is because the wheels have angular acceleration. Slow spin to a fast spin, angular acceleration. The car itself, the whole car is going slow and it's getting faster. It's having a change in velocity. So those are linked, all right? And that's why you can have tangential acceleration because you have angular acceleration. Now, we need to talk about one major concept before we go on, and we hit this so hard in first semester, and it is equally important in rotational. Remember that when we talked about speeding up, when an object was speeding up, all right, it was the acceleration and the velocity were same signs. We're same signs, and when we say signs, we mean direction. All right, if you were going east, positive velocity, you were speeding up, then your acceleration had to be positive. All right, when you had, and let me change markers here, when you're slowing down, we said, hey, your acceleration and your velocity were opposite signs, meaning opposite directions. So in other words, if you had a positive velocity going east and you were slowing down, then your acceleration had to be negative, all right, or vice versa. Up here, if you had velocity that was west, that means it's negative, then your acceleration had to be negative too, because same signs or same direction means you're speeding up. All right, perfect. Well, remember, acceleration and velocity were both vectors, and I got a little lazy with all my little vector signs, but they're vectors. Now, angular acceleration and angular velocity are not true vectors. They have magnitude and direction, but there's one law that they don't meet criteria, so they get thrown out as vectors. But anyway, they do have magnitude and direction. And remember, we talked about this. When you get to AP Physics C, you'll be using the right-hand rule, and then the rest of your engineering career, if you're going down the engineering path, you'll be using the right-hand rule. But in AP Physics 1, we keep it a little bit more simple, and we say, hey, positive is counterclockwise and negative is clockwise. All right, so it's the same concept for rotational motion, except when you're speeding up, now your angular velocity and your angular acceleration have to be same signs. So if I have this little device and I'm going counterclockwise slowly, and then I speed up and speed up, I have positive angular velocity, and because I'm speeding up, I have positive angular acceleration. All right, now again, slowing down, same thing. But now it's about your angular velocity and your angular acceleration. In other words, let's say that I'm going counterclockwise again, so counterclockwise, and I was going really fast, but now I'm slowing down. All right, counterclockwise, my angular velocity is positive. My angular acceleration is negative, opposite directions, because it's slowing down. All right, I could do the same thing. Let's say that I'm going clockwise now, and I'm going clockwise and slowing down. All right, well, my angular acceleration is negative because I'm going clockwise. So that means my angular acceleration has to be positive, opposite signs, or counterclockwise when we say positive for rotational. Okay, those are important concepts. My colleague Beth is following up with a big three. We're going to talk about those rotational equations, the rotational dynamics equations, I should say, and from linear to now rotational of those big three. Thank you for watching. I hope that you understand now a little bit better. Linear acceleration is just when an object is moving like down a ramp and slow and then speeding up, right? Versus angular acceleration, that change in how fast it's spinning, to tangential acceleration, which is because of the spinning and that angular acceleration, you also have linear acceleration like in a car. All right, perfect. Thank you. Have a great, happy physics. Oh, let's back this up a minute. First of all, if you like this video, please like it, subscribe, let us know. And we're glad you watched. Thank you and happy physicsing.